Hello and welcome to the MechSoft demonstration series, where you can see live demonstrations for real users and real-world applications. For more information about our products or to schedule your own live demonstration, just give us a call or visit us at www.mechsoft.com. This video shows the professional configuration of VisualCAM 2016 being used to perform positional 5-axis operations on a machine with an aggregate head configuration. Without further delay, we invite you to sit back and enjoy the demonstration.
Okay, so what I got is basically a very simple door panel, and we got some holes and features that you may want to machine it from the sides. Right? So it's probably not ideal to have the part stand up vertically to be able to mill this on a 3-axis CNC equipment. So you would probably want to use some kind of an aggregate head so you can basically program these features with the tool being normal to these faces. Right? Now, so if you're going to be programming by orienting the tool axis by locking into this plane and programming it, we call that as indexed or positional 3+2 or 5-axis index machining. So basically we are locking the tool axis to this given orientation and then programming it. So in order to do that in our CAM product, in our Pro configuration, we have a module called 3+2 which will allow us to create additional coordinates to program it. So the first step would be, let's say we would like to go ahead and program these these pockets, right? So first thing is we would need to define the machine tool as a 5-axis machine. And then we would also define the configuration as head-head.
Okay, what are the other configurations?
We have the table head, the table table. So a table would be like a trunnion style of 5-axis machine where your 2 rotational axes are on the table, which means part rotates. Or it could be a combination of a rotary table and a head, rotary head. For this particular application, since the part remains on the bed of the machine and the tool or the aggregate in your case is what's going to be rotating or tilting. So the aggregate heads could be a fixed angle aggregate head. It could be like fixed to 90 degrees, but then it can go like C0, C90, C180, C270 to basically be able to program these 4 sides.
Gotcha.
So a fixed angle is one of the angles is fixed to 90 degrees, right? Or it could be fixed to 45, or most cases if it's a fixed angle it's probably 90 degrees if I may be correct.
Yeah.
So we would define the machine tool in here as 5-axis, and we would define a primary axis and then the secondary axis, and then we can also specify the angle limits in here.
So primary is that it's bending about Z, and then secondary is that it's pointing in the X.
Yeah, the primary is rotating about the Z-axis. The secondary is rotating about X or Y. So if you go up to the help documentation in here, and if you look at the 5-axis setup, so the primary is the rotation about the Z-axis.
Okay, gotcha.
The secondary could be a rotation about the X or the Y-axis. We call it. It could be a C and a B or A and B, however the controls have been, labeled.
So if you did a fixed aggregate where it doesn't have a Z-axis, where you just have 2 outputs or 4 outputs, kind of thing, would you still put that Z as the primary, or would you?
Yes, for a head-head configuration, the primary would always be the Z-axis.
Okay.
And the secondary could be X or Y. Yes. Now in your case, what we need to do is we need to exclude the secondary from being output because the secondary is fixed on your aggregate head. Only the rotation of the C is what's critical.
Well, that's what I was saying. Some aggregates don't even have a C, right? Sometimes they just you just assume that you're going to machine one direction only, right?
So we can exclude them from being output, and then we can just output all the XYZ motions, transform them back to the world coordinates.
Gotcha. Okay.
So in order to do that, we make that the option to output all coordinates in local setup coordinate system is not selected or unchecked.
Okay.
Okay. And then if there's a gauge length to compensate for any offsets between the spindle axis and the aggregate axis, we can use that in here to compensate for it.
So the gauge length is how far the tip of the tool is from like the center of the center of the spindle.
Yeah, gauge length again is basically there's two parameters. One is the distance from the pivot point to the spindle face plus the tool length.
Right. Okay.
So the tool length is your tool definition. The distance from the pivot point to the spindle face is probably standard for a given machine tool and a head that you're using on a machine tool.
Right.
So the tool length would vary based on how far the tool is basically sticking out from the spindle face. So when you set this to a non-zero value, we take that into account.
So you set that, so that's with including your tool length.
This is excluding the tool length.
Oh, okay. Excluding. So where's the tool length? That comes in when you
define your tools.
That's in the tool setup. Okay. So what happens when you change tools out? You want to make sure that you set your tools the same length every time, essentially.
Well, if you change the tools, we automatically add the tool length to the gauge length parameter that you specify in here to compute the total gauge length.
Okay.
Okay.
So you don't have to update your code.
You don't have to update it here. You got to just make sure that the tools that you define have the tool lengths
right
in here.
Is in there. Right. Gotcha. Okay. That's easy enough.
Okay. Now, in the case of an aggregate head, if the aggregate is already at a 90-degree orientation and you only want to compensate for the offset in one direction, then what you can do is you can leave this as 0, but then you can specify an offset between the two rotation centers between the primary and the secondary. Okay?
Okay.
All right, so let's look at how we can program this space. So the next step is to select the post processor. I'm using a post called an OSI aggregate controller for an OSI, but you can write post for pretty much any controller that reads standard G codes.
Okay.
And we've already configured this post in here to basically use the C axis for the aggregate head, and then we've defined the macros, what to do before orienting the head to that given side or face. So the macros go in here, and the post can be tweaked around. Okay?
Sure.
Now we have a stock defined. We've defined a box stock for it, so basically a rectangular blank. And I'm going to display the stock right there. And that's where the 000 is currently set to.
Okay.
All right? Okay, so now what we're going to do here next is basically we will program this face in here. Now by default, your X, Y, Z axis orientation is in the same orientation as the world coordinate system, which is looking down from the top, right?
Right.
But we need to make sure that the Z axis is being normal to this face. There's a couple of different ways you can do that by going up to the setup and then selecting CSYS setup. So when we select this, we have controls here to orient the coordinate system. We can say we want to pick a surface, and we can pick the surface. Or we can say spin angle. We can use a 90-degree angle and say rotate it about the x-axis. So which means it's rotating the coordinate system about x. Your z-axis is now being normal to this particular face. Now in this particular case, we know that they're all at 90-degree orientation, so which is probably pretty straightforward to set it up right there, right? And then I pick OK, and you notice that the coordinate system is rotated. Now if I hide the display of the world coordinate system, you'll see that the machining coordinate system is rotated from the world coordinates to the rotated face.
Gotcha. So you want to orient the Z pointing into the face or out, or
yeah, so we want the Z-axis to be normal to this face. So if the Z was pointing in the opposite direction, then the tool would be approaching from the other side. So in this particular case, you want the tool to be approaching from the direction of the Z-axis arrow.
Gotcha. Okay.
So we got this. We have it oriented right there, and now you can see that the setup is oriented, And now we are ready to program some toolpaths. I could say let's do a pocket operation in here. So we'll select 2 axes and pocketing, and I'm going to select the drive view geometries as these geometries right in here. I can even go and pick these geometries right there and then press enter when done. The next step is to specify a tool. I have an end mill that's about 3 inches in length, as you see right there. I also have my feeds and speeds set for it. And then we go to feeds and speeds to have it loaded from the tool. We got the clearance definition. You will notice that your clearance plane is parallel to your rotated coordinate system. As you can see now, the clearance is in the same orientation.
Oh, awesome. Okay.
If you want to change it, you can always change it. You can say you want to keep it at least 2 inches clear of it. You can specify
Gotcha.
right there. The next step is basically to specify your cutting parameters in here. You can specify the tolerances, leave any stock, side stock or wall stock around these parts. If you're pocketing, if you want to finish it to the exact size of the pocket, you can set the stock to leave as 0. You can specify your cut pattern, your cutting direction, your step over. So very similar to how you are used to programming for 3-axis operations. Now the next step is to specify or determine determining the depth in here. Since I'm not familiar with how deep this pocket is, I can use the pick option, and I'm going to use the end object snaps to snap to 2 points, 1 and 2 right there. So the depth is basically also determined based on a rotated coordinate system setup that you have. So it's 1 inch in depth, and I could say I want to go in 1/4 inch steps. Specify entry and exit, any additional parameters, and then you pick generate. And there's your pocket toolpath right there.
Interesting. So can you pick the depth of that pocket just by clicking the faces? That's often what I find myself doing.
I probably believe you were running the plugin in Geomagic Design, right?
Yeah, correct.
In the standalone system, rather than picking faces, you can actually just snap to an endpoint or a near point on an edge.
Okay, so that's a standalone system feature.
You can snap to an edge or an endpoint or a near point using all of these object snaps that you can find right down below in the status bar. So I just snapped to the 2 endpoints. Okay? So we got this side program. Now let's go take a look at the simulation in here. So I'm going to select the stock. You can see the stock right there. Let's select the part, the operation that you program, and then you hit the play button. So you can now see that the tool is oriented in the orientation of the same as the rotated coordinate system.
Nice.
So it retracts, and we chose the other larger pocket right there. So it's programming the pocket over there, and then the hole right there.
Perfect.
Okay. Now let's say we want to go ahead and program the side over here, the longer side. So there's a couple of ways to do it. Again, you can go back and click on a new setup, coordinate system setup, and then you can say you want to rotate it. In this particular case, I could say select a surface, and I can pick the surface right in here. So I can pick a point on a face right there. In this case, it's a poly surface. I need to explode it, or I could use an option called select a planar curve, and we have a planar curve right there. And you'll now notice that the z-axis is being normal to that face. And if you also need to rotate it about the x and y, you can rotate it, and you pick OK. So you can now notice that the z is normal to this face.
Great.
Now I can make a copy of this operation. I'll paste it down below the new setup I created. I'm going to go modify this, and I'm going to go select the features to program from this specific orientation. Right, I can also pick those holes, the circles as well. So once you have these selected, now we can go ahead and specify your tool, the feeds and speeds, now your clearance. Notice the clearance is in the same orientation. And it's accounting for the stock max plus 2 inches in the orientation of the rotated coordinate system. Now let's go ahead and make sure the depths are correct in here. So I'm going to pick 2 points. And that's it, right there. And then you hit generate. So now we have the holes programmed on these sides. So now, if you take a look at this toolpath in here, this is where the tip of the tool is, right?
Mm-hmm.
So you're going to be zeroing it out, this tip over here to this face right there. Right? When you start the first operation, that's where you're going to be zeroing it out. That's your XYZ0 technically for cutting all of these parts, right?
Okay.
So if you know this offset in here, this distance offset,
Mm-hmm.
and the offset between the spindle, the main spindle axis, you can enter that, the distance between the rotation center offsets right in here. You can say it's offset in the X by a certain distance right there. And that'll get compensated in when you post-process it. Now, I'm going to post-process these operations in here, select the machining job, right-click and then select Post All. I'll hit Post, and you'll notice that it posted it out, and then for the first setup it says the C is at 0. So it's considering that the C is at 0 when it's the tool is normal to this particular face.
Right.
And you can see that the coordinate systems are automatically transformed into the world coordinates.
Mm-hmm.
So the next search we want to do is for the next parameter for the C value. Okay, so now if you take a look at it over here, you can see that the C is rotated to 90 degrees to program this particular face.
Mm-hmm.
And there it is.
So if you don't want to rotate your head, you just ignore that? Or,
We can exclude this from being output in the code.
Mm-hmm.
So, and then you can basically just have the XY motions, XYZ axis motion. So you manually basically output each setup individually to the machine, right?
Excellent. Yeah.
You post the first setup, and we can exclude the C from being output, C axis coordinates from being output in the posted code. And then you manually orient the aggregate head to the next face, and then you post it out. Now it's interpreting all the coordinates.
Out, you do that manually, or you write it in?
We can go into the post processor.
There's a setting. Gotcha.
And then go over to the setup, and then we can exclude this C axis parameter from being output.
I gotcha. Easy. Okay.
Now all of your coordinates are still interpreted based off this origin right in here. So that's just XYZ origin.
Mm-hmm.
So it's computing all your toolpath coordinates based off the origin that you define. So if you have the C can rotate automatically, then you can basically post all the setups in one file.
Excellent.
So that's how you'd go about programming it. This is called 3+2 machining, or also known as indexed 5-axis machining. So if it's a 5-axis machine tool, you could have a C and a B. In the case of aggregate, there's only one axis. It's typically a C axis for fixed angle aggregate heads.
Mm-hmm.
And if there's an offset between the rotation centers, we should be able to handle it as well.
Gotcha. Interesting. And then you can always program, you can always run a different tool in your aggregate so long as you know the tool length, and you can put that tool on the tool table and just run different tools also.
So basically you're programming a 2 or a 3-axis operation, and even if you have like a sculpted feature in here, like a radius feature or a sculpted bottom, you can still program a 3-axis toolpaths.
Oh wow, okay. And so you're really just treating it, so you still have, so you have your entire library of 2 or 3-axis moves or operations that you can run.
Absolutely. You can apply all of your 2-axis methods and your 3-axis methods when you're programming indexed 5-axis or positional 5-axis.
Gotcha. That's awesome. Okay, excellent.
Do you have any other questions before we wrap up?
No, I think that's good. That really answered everything.
Okay, so the critical pieces of information that you're going to be entering is your offsets between the rotation centers. So if you need to have it compensate for that, so you can say that the, if the tool tip is a 0, 0, then the spindle rotation center could be off in the x-axis by, or y-axis in this case, by a certain distance in here. So you could say maybe -5, for example. Right? So this could be the location of the spindle center when the tool tip is over here. Right?
Mm-hmm.
So when you compensate for this and post-process it, the posted code will automatically compensate for the offset distance as well.
Is there a way to do like a tool change mid-program with this? Like a manual tool change?
You could still do a tool change. Yes, absolutely.
You just have to set your machine to not automatically change tools, essentially, and kick out, do like a pause, essentially.
Yeah, here you can see that the tool number is being called MO6T1. So if you have a tool change, it'll be MO6 followed by whatever the tool number you've assigned to.
Oh, that's awesome. Okay, that's very helpful. Very good.
All right.
Well, I think that was what I needed to see, and it definitely does what I was hoping it would do.
That's great to know.